Morning session. And the first speaker of today, Vyron Vellis, and then he will talk about Cantor Julia sets.
Thank you for sharing the session. And, thanks to the organizers for inviting me. It's an honor to be here. I don't consider myself part of the complex dynamics group, but I've learned so much in this conference, so thank you for organizing. So today I'm going to talk about joint projects with Cantor Julia from University and Dan Stewart from St. Paul College. So I'm going to start with the definition of the counter set that everybody knows. And a fact that
you all know, Julia sets are closed and have no isolated points, which from a topological point of view means that the most simple thing that a Julia set can be is a Cantor set. Or in other words, every Julia set has a Cantor set. So towards the understanding of Julia sets, one must first sort of understand what Cantor sets can arise as Julia sets. Now, this fact was later generalized further for rational functions. And I had a discussion yesterday about how hard was this to disseminate math back in the day. So this is a brilliant example. There were 3 papers the same year that they proved exactly the same thing, and they had almost the same title. So Remenko, Hinkanen, and Maneda Rosa independently proved that Julia set of rational functions are uniformly perfect. Now, uniform perfectness, if you haven't seen the definition before, says that every point is an accumulation point, but the accumulation cannot happen too fast, okay? At most in a geometric fashion. And now the next question is, okay, we know that Cantor Julia sets must be perfect, or for rational functions uniformly perfect, but what can they actually be? And some examples have been mentioned earlier in the conference. Here are 2 more examples. Of course, if you take any point C outside of the Mandelbrot set, then Z squared plus C produces a Cantor Julia set. They may not look like Cantor sets, but they are. However, the most standard of the Cantor sets, the Cantor set, is not a Julia set of a rational map or even a holomorphic map. Now, I haven't seen any proof published of these facts. My co-author, Alistair Fletcher, has a very nice proof, and I'm just gonna leave it as an exercise if you wanna try it. The idea is that the standard Cantor set has a lot of symmetries that cannot be preserved under holomorphic maps. And although this fact is not unexpected, it is quite disappointing. And in fact, we conjectured with Alistair that, and we worked for a while, that this is a pattern. In fact, not just the standard Cantor set, but any self-similar Cantor set cannot be the Julia set of a rational map or a holomorphic map. Here, when I say self-similar, I mean an actually honest-to-God self-similar, that you can write it. So self-similar for me means that you can write your Cantor set as the disjoint union of Cantor sets, each one being a rescaled copy of the original one, such as the standard Cantor set. All right. Now, from a fractal geometry point of view, which is my area, complex dynamics, classical complex dynamics, have 2 restrictions. The first one is the one that I've already mentioned, that canonical examples, such as the standard Cantor sets, and probably the Sierpinski carpets, and probably the Sierpinski gaskets, are not part of this theory. And the second restriction is that, as we know, there are no holomorphic, non-trivial holomorphic maps in higher dimensions. This is usually known as the Liouville rigidity theorem, but it was proven really by Gehring and Reshetniak, so I'm just going to call it Gehring-Reshetniak rigidity theorem. So there is no theory in higher dimensions, and there are so many fractals in higher dimensions that could arise, and we will see that they will arise as Julia sets. So these 2 abstractions, among other things, have led to a generalization of holomorphic maps, which we call quasi-regular maps. They have been mentioned before in a slightly different context. So what do I call a quasi-regular map? So a quasi-regular map is an orientation-preserving map, which is in the Sobolev 1n class. That means that it's differentiable almost everywhere, and its derivative is n-integrable locally. And it satisfies this distortion inequality for almost every point. Where here in the middle I have the Jacobian. And geometrically, what this condition says is, so let me put the picture. So take an infinitesimal ball, a ball of very small radius, and then it's mapped into something like that. What I have on the left-hand side, this one, is the biggest possible stretch. So that would be capital M. And what I have on the right-hand side is the smallest possible stretch, which is little m. So what this distortion inequality says is that the biggest possible stretch compared to the smallest possible stretch are comparable. Or in other words, as we like to say, quasi-regular maps map infinitesimal balls to infinitesimal ellipsoids of bounded eccentricity. Okay, they cannot stretch too much things locally. Now, in 2 dimensions, holomorphic maps are exactly the one quasi-regular map. So this is a generalization. By the way, I failed to say that there is a constant here which describes this distortion. And when the distortion is 1, then you simply get the good old Cauchy-Riemann equations. And it was also mentioned earlier in the conference, when you're in 2 dimensions, you can define quasi-regular maps in a different way. So that's Stoilov's theorem. It says in 2 dimensions, quasi-regular maps is the composition of a quasi-conformal map and a holomorphic map. Okay. So this is an alternative definition for 2 dimensions. And before we start doing dynamics, we need one more thing, right? When you compose a K quasi-regular map with itself, you get a quasi-regular map, but the constant becomes K squared. And as you keep composing, that constant goes up. Of course, this is no problem for holomorphic maps because 1 times 1 times 1, that's 1. You always get the same thing. But it is a problem in the general case. So what we need and what I'll be dealing for the rest of the talk is a subclass of quasi-regular maps specifically designed for dynamics called uniformly quasi-regular, or simply UQR. So I'm going to call an orientation preserving map a UQR map if F and all of its iterates are quasi-regular with the same constant. This is still a generalization of holomorphic maps, but we will see that there are a lot more. And a lot of the examples that I mentioned earlier of Cantor sets come from hyperbolic rational functions. And in fact, there was a theorem of Hasinski and Pilgrim that said that if the Julia set of a hyperbolic rational function is a Cantor set, right, then it must have nice properties, which we will study later. So that sort of led us to define a notion of hyperbolicity in this class of UQR maps, which the definition is exactly the same as it is for rational functions, right? So here's the definition. A UQR map, I'm going to call it hyperbolic if the Julia set does not meet the post-branch set, or I guess here it's called the post-critical set. Okay, so the branch set is the set of all points where around that the map fails to be a homeomorphism. Another thing is that a quasi-regular map, which is a homeomorphism, is a quasi-conformal. All right, so let me now pose the question that I'm going to be dealing for the rest of my talk. Which Cantor sets are Julia sets for hyperbolic UQR maps? Okay, so as I mentioned, Hasinski and Pilgrim proved that if you have a hyperbolic rational map and the Julia set is a Cantor set, then it must have very nice geometric structure. So what is this geometric structure I'm talking of? I'm going to call it quasi-self-similarity. It's not exactly self-similarity. And here's the definition. So a Cantor set is quasi-self-similar if for any point and for any scale, I can find a subset of my Cantor set that contains X, and its diameter and its distance from the rest of the Cantor sets are both comparable to R. Okay, in my picture, this looks as if it has area, but it's a bad picture. Okay, this is supposed to be a subset of the Cantor set, and this is supposed to be the rest of the Cantor set. So in other words, there are holes between the pieces of your Cantor set which are not too big, neither too small. And if the word quasi-symmetric means anything to you, I will mention that there is a theorem that says that a Cantor set is quasi-self-similar if and only if it is quasi-symmetric to the standard Cantor set. Yeah. No, you just need, you only care about the specific scale. And the way it is that uniform perfectness is the weakest notion, quasi-self-similarity is stronger, and self-similarity is the strongest of these three notions. All right, so let's see some examples. All my examples are going to be in these slides one-dimensional, but later on we will see higher dimensional examples. So the first example, you take the unit interval, you remove the middle 1/4, then in the remaining ones, you remove the middle 1/4, and so on and so forth. So the 1/4 I have here is what you remove on each step. This is, of course, self-similar. That's not hard to prove. And now do the same, but what you remove is neither too big nor too small. So you have a sequence of positive numbers that does not approach 0. So you're not removing, yeah?
This joint union of its own copy, but this joint you said, so the Sierpinski carpet and the Sierpinski
joints.
joint, that's
You
what,
have the
so
number.
they are not self-similar for
Yeah,
you.
exactly.
They are not self-similar for you.
Well, they're
No, they are self-similar, but I gave the self-similarity for Cantor set specifically.
Sierpinski is
Yeah, it is not count.
Right, so suppose that in each step you remove the middle interval of ratio A3, A4, etc., and this is neither too big nor too small, then this is quasi-self-similar. And this is another example. Take one ball and put the standard Cantor set. Take another ball, this joint, and put this self-similar set, and take their union, right? This is not self-similar. You have two different things. But as a union, it's quasi-self-similar. Next, now here we have an example where we remove less and less and less, right? So in the first step, we remove the middle 1/2. In the second step, the middle 1/3. Then the third step, the middle 1/4, and so on and so forth. So I'm making the hole smaller and smaller. And what I violate here is this fact, right? I cannot find subsets at any scale that their distance from the rest is large. So this example here is uniformly perfect. The holes are small, but not quasi-self-similar. And my last example is something where I remove more and more, right? So I keep removing bigger and bigger pieces. So this is not even uniformly perfect. Okay, so now let's go back to Julia sets. And here we have two geometric abstractions for Cantor Julia sets. The first one is a theorem of Alistair Fletcher and Dan Nix, which generalize the three-paper theorem. Right? The three-paper theorem I mentioned at the beginning said that Julia set of rational maps are uniformly perfect. They improved it for UQR maps, and this is, of course, in every dimension, not just in 2 dimensions anymore. And 10 years later, with Alistair, we proved that if you replace UQR by hyperbolic UQR, then you must have quasi-self-similar. And this generalizes the theorem of Hasinski and Pilgrim. All right, so now let's see some examples of Cantor Julia sets. The very first example, so the rest of my talk is going to be 2 dimensions, which is pretty easy, everything is clear. 3 dimensions, which is pretty hard, and then higher dimensions, which is terrible. All right, so in 2 dimensions, the very first example was by Ivanets and Martin, who proved that the standard Cantor set is a Julia set of a hyperbolic UQR map of S2. And remember, this is not true in the holomorphic. So the way they proved it, the result itself is not so important compared to the methods that they use to prove it, which today we call it the conformal trap method. And it's a very smart method. So let me talk a little bit about how the proof goes here, okay? So the UQR map that they constructed is a composition of 2 things. A map phi, which is an inversion, and I'm gonna explain to you in a moment, and a map G, which I have in the slide. So the map G is defined as follows. Outside of the blue disk, the black disk, and this blue disk, the map G is simply doubles the angle by 2. Okay, so this black disk is mapped here, and these 2 blue disks, they have their angle doubled. They're mapped into this dotted blue shape. Okay, inside these red disks, these 2 red disks, it's simply a translation that maps everything to this red disk. And in this red disk, it's a translation that maps everything to this disk. And then the only place left to define is this annulus, and this annulus, where you use a quasi-conformal extension in the spirit of Sullivan. So now I have defined my function everywhere. This is G. Now phi is an inversion with respect to this small red disk. Okay, so now let's see what happens. If some element, if the orbit of a point ends up inside this red disk, then it stays here forever. So this is what we call a conformal trap. It's trapped inside this red disk. Indeed, if it ends up here, then G is going to map it by translation here, and then the inversion is going to take it back in. So anything that ends up in this red disk stays there forever. And then the next question is, what does end up there? Okay, if you are outside of these 2 red disks, then the map G is going to take you outside of this red disk, and then the inversion is going to take you in. So any point outside of these 2 red disks is eventually trapped. But it turns out that even in these red disks, there are points who are eventually trapped. And when you do a careful analysis, one can prove that, in fact, there is only a Cantor set formed by a defining sequence of disks starting from these 2 that is not trapped, and that's the Julia set. Everything else is going to be eventually trapped, and that's going to be the Fatou set. Of course, kind of lied here. That does not give you the actual standard Cantor set, but there is a way to work around this. Yeah.
Blue and the black, it's a doubling. It's a doubling.
It doubles in here.
So the real line is the positive reals are preserved.
The positive reals are preserved. Yes.
Okay, and then you said that that little red disk is gets translated into the dotted form.
This one, yes, it's translated.
You get translated to the reals, and the reals are preserved.
No, not all reals preserved. Only the reals outside of the black. Right, the map G is defined outside of this black disk, not inside.
Oh, so the red one there, which is close to -1, of minus
Yeah, yeah.
1, so it gets translated to 1.
Yeah.
Then there will be a real line which is kept instead of 1. So how can it be trapped in the other one?
So let's see the real line. Let me think about it. Let's talk after that. Thanks. All right. So okay. Later on, Fletcher improved the Ivanets Martin, proved that not just the standard Cantor set, but in fact any self-similar Cantor set is Julia of a hyperbolic UQR map of S2, and then with Alistair, we further improved this theorem and sort of clear the situation in 2 dimensions completely. So a Cantor set is a Julia set of a hyperbolic UQR map of S2 if and only if it is quasi self-similar. So we know exactly what Julia Cantor sets can be. Now let me pull the curtain and say that this theorem actually follows pretty easily from a uniformization theorem by McManus that says that quasi-self-similar Cantor sets are exactly the sets for which there is a global quasi-conformal map that maps it to the standard Cantor set. So once you have this theorem, essentially the way you get this result is you have a quasi-conformal map, you have some sort of a map coming from Ivanitz and Martin, you conjugate this map with your quasi-conformal function, and you obtain a UQR map that does the trick. There are some details to check, but this is the basic idea. So going now to 3 dimensions, one can ask if this is the same in higher dimensions. Like if you have a quasi-self-similar set in 3 dimensions, can you produce a global quasi-conformal map? That would be great, because then you can conjugate with this map and have the same theorem in every dimension. But I don't have the same theorem in every dimension, so the answer is probably no. And the reason is that in higher dimensions, Cantor sets can be very complicated. So let's start from some topological facts here. We know all Cantor sets are homeomorphic to the standard Cantor set, but are they ambiently homeomorphic? Is there a global map? So I'm going to call a Cantor set tame in Sn if there exists a global homeomorphism that maps it to the standard Cantor set. And in dimensions 1 and 2, by an old theorem of Moyes, everything is tame. Okay? And specifically for tame Cantor sets in 3 dimensions, we have a theorem. So if you have self-similar and tame, it's a little start here, I'll explain. Cantor set in 3 dimensions, then it is the Julia set of a hyperbolic UQR map. Now, the start here is because we have some extra technical conditions, which I think we can drop, but we haven't dropped so far. I don't want to get into too many details because that's not important. And there is a hope that this self-similarity can be replaced by quasi-self-similarity. And now I'm going to call a Cantor set wild if it's not tame. So how does a wild Cantor set looks like? The most famous and the first example of a wild Cantor set in S3 was due to 1-to-1. So this is the basic idea. You start from a solid torus, and inside the solid torus, you put a chain of solid tori, which are rescaled copies of this guy inside here, linked with each other, forming a chain like that. Okay, so imagine this living inside here. And now you play the same game. Inside each one of these solid tori, you put another chain of solid toris in the same fashion, and you get that. And you continue. Okay. The limit set is a Cantor set. It's self-similar. It's easy to prove it's self-similar. I mean, the whole set is just a union of these copies. And Antoine proved in 1921 that this is wild. So why this is wild? Well, one can compute, which is not easy, that the fundamental group of the exterior is non-trivial. In fact, if you take a loop around this Cantor set, you cannot contract it without hitting the set. Which, if it was tame, you wouldn't be able to do that, because for the standard Cantor set, you can contract things, but you cannot contract things here. So the next question now is, can Julia sets be wild? And if yes, how topologically complicated can they be? Okay, so I'm going to open a big parenthesis now for 2 slides only, I promise, and explain to you a topological index that measures how wild a wild Cantor set can be. Okay, this is an index introduced by Zelko in 2005 called the genus of a Cantor set, and that works only 3 dimensions. All right, so the idea is this: you start with a Cantor set in S3, and there is a theorem of Armentrout that says that you can construct your Cantor set as an infinite intersection of handle bodies. And a handle body is a three manifold with boundary, or a cube with handles, if you prefer. Okay, so every Cantor set is the limit of a defining sequence of handle bodies. So, for example, if you take the standard Cantor set, then you can construct it using only balls, right? And so on and so forth. So that's a defining sequence. And a defining sequence for the Antoine necklace is already given in this picture, right? You use a defining sequence of solid cubes. However, defining sequences are not unique. In fact, for the standard Cantor set, this is one defining sequence, and another one is if I attach a handle, right? And maybe I'll attach here two handles, and another handle here. Maybe this is a ball, maybe this has three handles. So I got another defining sequence which produces exactly the same set. But one might say, why would you attach handles? That would be idiot, right? And that's exactly the spirit of Zelko's definition, right? So the genius of a Cantor set is you have a Cantor set and you try to find the defining sequence, which is the most simple topologically that can create the set. So that's a formal definition. You have a Cantor set, you go over all the defining sequences of this Cantor set, 4 by handle bodies, and you calculate the supreme of their genera, and that will be your genius, okay? And then there is a definition, which I'm not gonna give formally, but you can sort of deduce it of a local genus, right? For any point, you can, the local genus is pretty much the same thing, but you only care about the local situation, only those handle bodies that approximate the specific point. All right, so let's see some examples of Cantor sets with genus. So the first one, Cantor sets, of course, are tame if and only if their genus is 0. That's easy to prove. And the contrapositive of this fact, a Cantor set is wild if and only if its genus is bigger or equal than 1. The genus of the Antoine necklace is exactly 1. Why is that? Well, it's wild, so its genus is bigger or equal than 1. You can construct it with genus 1 objects, so its genus is less or equal than 1, so its genus is exactly 1. Now, constructing sets of higher, Cantor sets of higher genus, this is very challenging. And Zelko in his paper constructed for every n a Cantor set of genus n. So let me give you the construction for n equals 3, Zelko's construction. Right, so the idea is you start with a genus 3 object, let's call it a flower. Okay, and inside here, I'm gonna put in the middle a flower like this. And I'm gonna put a sequence of solid cubes going around linked like this. Now, in each of these solid cubes, you put an Antoine necklace. Inside this central flower, you put this picture again, and you iterate this process. So Zelko proved that this Cantor set has genus 3, but there is only one point of local genus 3, and that's the center. Every other point has local genus 1. Okay, and you can do this construction for every n. Also, this is quasi-self-similar, but it's not self-similar. All right, so that was Zelko's construction. And now back to Julia sets. I close the parenthesis. And this is the first of our results here with Alistair and Dan. So suppose that you have, suppose that X is a Cantor set and it's also the Julia set of a hyperbolic UQR map. First one says that the genus must be finite. I mentioned that there are sets of any genus, but you can also make Cantor sets of infinite genus by just accumulating Cantor sets of arbitrarily large genus. But if you have a Julia set, the genus has to be finite. And this result is not very surprising given the fact that we already know X needs to be quasi-self-similar. So it has some sort of finite representation. So this is really not surprising. But the next one is very useful. it says that the local genus, the set of points where the local genus is equal to the top genus must be dense inside the set. So what does this mean in practice? Well, let me give you two examples. Put the standard Cantor set in one ball and the Antoine necklace in the other ball, right? The union of these two things is a quasi-self-similar set, but on the Cantor set, on the standard Cantor set, the local genus is 0. On the Antoine necklace, the local genus is 1. They don't satisfy this property, so it's not the Julia set of a hyperbolic UQR map. And another example is Zelko's example, the one I mentioned over there. That's also not the Julia set of a hyperbolic UQR map, simply because there is only one point of high genus. Everything else is genus 1. Okay, so I told you what we cannot do. So let's see now what we can do. Let's see some examples of wild Cantor sets. The first one is by Fletcher and Wu, who proved that the Antoine necklace is the Julia set of a hyperbolic UQR map of S3. And last year, Alistair and Dan proved that there exists a hyperbolic UQR map of S3 where the local genus is 2 for every X. Now, I want to emphasize how deceivingly hard this theorem is. And let me do the naive approach of how to construct this Cantor set. So the naive approach is this. We want to start with an object of genus 2. And inside here, I want to put objects of genus 2 linked with each other. So let's do that. This is a genus 2 object linked with this genus 2 object, etc., forming a chain, which I will iterate again and again and again, right? That's guaranteed to be self-similar. And around here, the picture is gonna look like this. Oops. Right? You have two chains like that. So I took this picture in Finland, and as soon as I saw these two chains, I immediately thought of their paper, and I sent it to them. All right, but what is the problem? The problem is that you could replace this genus 2 object. Maybe I should use a different color here. You could replace this genus 2 object by a genus 1 object that contains your whole chain. So why did I need the genus 2 object? I didn't. This Cantor set ends up having genus 1, not genus 2. And the remedy behind that is you have to take these two chains and click them in a 4-way link. That would be the only way that you cannot replace a genus 2 object with a genus 1 object, let alone proving that this is a Julia set of a UQR map, which is also very hard. So that was their theorem. And the theorem I want to talk about today is the generalization of their theorem, where we prove that for every natural number, there exists a hyperbolic UQR map that the local genus is n for every point of the Julia set. So our construction is slightly different than the genus 2 case, and let me try to give you some idea of how the Cantor set works. I have to apologize, of course, my pictures are terrible. They're all 2-dimensional, but this is a 3-dimensional object. So let's see. All right, so I'm gonna do the construction only for n equals 3. And we start with this set here. This is a 1-dimensional set. Notice that this is 3 times as long as these two, and I'll explain why is that. And then I thicken this in 3 dimensions. Again, this looks a 2-dimensional picture, but think of a 3-dimensional ladder. Okay, so this is a thickening, and this is my genus 3 objects. And what I would like is to put genus 3 objects inside this one, linked in some weird way. Okay, so think of this way. You take this ladder, I'm going to call this a ladder, and you rescale it, and you place rescaled copies of this ladder vertically in this picture. Okay, so you put a chain of ladders inside here vertically, you put a chain of ladders inside here, and you put a chain of ladders linked vertically again inside here. And here I'm going to show you just the projection. So think of these ladders. If your ladder lays flat on the floor, you put the smaller ladders vertically. And the dotted one means that you lift the ladder slightly so that it links with the solid one. So this is the top of the ladder as you're looking from above. This one is lifted slightly so that it links with this one, and each one links with the previous one and the next one. Okay, and now this is just a chain of ladders from this part of the ladder, and then there is another chain coming from this part, and these two chains, this one and this one, they have to link with each other. So this is how it's going to look. Okay, so we have chains of ladders linked with each other. And the blue ones are the ladders coming from the right. The black ones are the ladders coming from the left. Dotted means it's slightly up so that it links with the solid one. And basically that's the picture. And now, as soon as I gave you the first step of the construction, then it's easy to iterate. Inside each smaller ladder, you put smaller ladders and so on and so forth. And eventually you get a Cantor set, which has genus 3. Well, I'm not going to talk about it. There's a lot of algebraic topology on that. But I want to maybe give you an idea of how does the UQR map looks like in this case, okay, and why this is the Julia set. All right, so I want to construct for you the UQR map that produces this weird Cantor set as a Julia set. And the first step that I need is a quasi-regular map between the first ladder minus its children to a ball minus the first ladder. So think of a large ball. So I have a ball B here, and inside B, I have my ladder. Sorry, that was the only picture I wanted to do. You can turn off the lights again. Sorry. And I want to map T, the top ladder minus the smaller ladders, which is a very complicated topological object, into this one, which is a lot more simple. Right? So how do we do this? I'm going to do the proof by pictures. This is your top ladder. I have not put the smaller ladders because that would make my picture too complicated, but think of them being inside there. And what I do is an involution that sort of folds this guy into this, right? So gray goes to gray, pink goes to pink, blue goes to blue. So it's an involution that folds it, okay? Again, there are ladders inside here, smaller ladders, which I don't put. Then the next step is another involution with respect to this axis that folds this into a genus 1 object. And there it is. Now I put the smaller ladders inside here. Then the next step is I want to normalize it so I can make this round and the ladder sort of equally spaced. And I get that. And then the next step is another involution of very high degree that maps all the solid ladders into one solid ladder and all the dotted ladders into one dotted ladder. And it gives you that. So this is a genus a solid torus that has one ladder linked with another ladder in 3 places. And then the final thing is an involution with respect to this axis that folds this thing and maps the dotted ladder into the top ladder. And it gives you that, modulo some bi-Lipschitz maps, which are easy to construct. All right, so this was the first step, and now I want a UQR map. So here is how we construct it. I'm gonna split S3 into 2 pieces. I have S3 minus this ball B, B minus the ladder minus the smaller ladders and the smaller ladders. And I'm also gonna split in the same way. B prime is a ball, not gonna draw anything. B prime is a ball that contains this ball, a larger ball. And the map F is gonna be, well, I'm gonna use similarities. I already mentioned this is a self-similar set. So I'm going to use similarities from Ti to T. From T minus union Ti to B minus T, I'm going to use the map that I just showed to you. And this is a very high degree map. So one can construct a UQR power map, whatever that means, of the same degree here. And then you glue these two maps together by the Bernstein-Enbons extension, which is an extension for piecewise linear maps on manifolds for 3 dimensions. And that's the map. So what happens now, roughly speaking, is that if you have a point which is not on this Cantor set, then eventually that point will escape to infinity through the sequence of maps, right? If it's here, it will go here, and from here, here, and so on and so forth, and eventually it will escape to infinity. So the only points that will not escape to infinity are going to be these Cantor sets. Okay. All right, I'm going to skip the next slides, and I'm just going to go to 4 dimensions. So the situation in 4 dimensions is very complicated. There exist wild Cantor sets, which are very hard to describe, but we know pretty much nothing about their geometric structure. The first result I want to say is the best we could do with Alistair. So we proved that if you have a quasi-self-similar Cantor set on Sn, then it's a Julia set of a hyperbolic UQR map of Sn plus 1. Right? That's the bad thing about our theorem. We have to go 1 dimension up. And the reason why we go to a higher dimension is that anything on Sn, as bad as it may be, it's tame in a higher dimension. Okay? There is a quasi-conformal taming theorem for higher dimensions. So that's why we have 1 dimension up, which we don't like, but it is what it is. Now, we do this because we are afraid of wild sets, right? And wild Cantor sets indeed exist in every dimension, very complicated construction. But it is unknown, 1, whether they can be self-similar, and 2, even when whether they can be quasi-self-similar. Okay, there is only 1 example for n equals 4 of a quasi-self-similar wild Cantor set, and this is due to Pekka Panka and Yang Mei Gu, who constructed a wild quasi-self-similar Cantor set in S4, and they proved that it's a Julia set of a hyperbolic UQR map. This is a really hard theorem. Well, I guess main difficulty is producing this Cantor set in first place. All right, so I'm gonna end with 2 questions, which are very easy, but I don't know how to solve. The first question is, suppose that I have a self-similar Cantor set. Is there a hyperbolic UQR map that produces this set as a Julia set? For tame sets in S3, the answer is yes. Anything else, we don't know. And the second question is, if I replace self-similar here by quasi-self-similar, then we already proved that the answer is no. There's not always a hyperbolic UQR map. But is there just a UQR map? So if you have a quasi-self-similar set, Cantor set in Sn, is there a UQR map that produces this as a Julia set? I think they are both very interesting and quite hard. And with that, I'll finish. Thank you.
Questions or comments? This night talk? 1 and 2.
I don't know if you mentioned this, but can there be wild Cantor sets of genus infinity, meaning that on each step it's finite, but then
yeah. In fact, the way to construct it, let me see. So one way of constructing an infinite genus is this: you take a sequence of balls, and here you put a Cantor set of genus 1. Here you put a Cantor set of genus 2. Here you put a Cantor set of genus 3. So that's going to have infinite genus. But there are other ways as well, of course. You can... maybe I shouldn't talk too fast. Well, this is one way.
Beginning of your talk, you mentioned about realizing Cantor sets as Julia sets of rational functions. I was wondering if it's easier, instead of being the whole Julia set, to just be like a subset, so that each connected component is a connected component of the Julia set. Right?
Connected components,
Like for example, if it's connected, like take the Sierpinski triangle, right?
right?
Is it possible to find rational functions for which this is a connected component of the Julia set, or is it clear that this cannot happen?
I think if
The
the
Sierpinski gasket is not a Julia set, it's unlike that it can be a component of a Julia set. I don't know. In my mind, I have that. Although again, I'm not in complex dynamics, but I thought that rational functions sort of disturb things a lot. They wouldn't preserve so many lines in a sense.
So we have a result about realizing these sorts of things as connected components of Julia sets of meromorphic functions.
okay,
And then realize every closed set without interior.
I see.
So I don't know if that would help.
I don't know.
Any other questions or comment?
I just like to follow my comments. In fractal geometry, we have a notion of what is self-similar, and not even for the Cantor set, it is the same. So when you say self-similar Cantor set, it is possible that it is really a Cantor set, but the cylinders overlap. So here you use self-similar in a way which is not as we use it in fractal geometry.
Yeah, I guess I meant to say self-similar with an open set condition.
Still, okay, that's still not the same, but it is separated. So somehow when this coding map is what you mean, it is that this coding map is a bijection. So this is but I want to say that I very much like this whole thing, but it's a little bit confusing because people generally know what is the most interesting Cantor sets are the ones with overlapping cylinders.
Okay.
So that's what I want.
I have said when I say self-similar, I mean the attractor of an iterative function system with the open set condition and similarities. Okay.
Okay. Any other question or comment? So if not, thanks, speaker again. Self-similarity from the last stage, and I think we start again at 11.